Ladies and gentlemen, boys and girls, welcome to another episode of Transparent Physics. In this lesson, we are going to continue our series on energy, work, and power. And here's the main event, people, conservation of energy. Basically, one of the most important topics in this series, and one of the most important topics in physics in general, I would say. Let's take a look. Get a little bit of housekeeping out of the way. If you're watching this video at any time and you're like, hey, I really like what he said right there, maybe click the like button. If you have any questions about what I say or how I say it, leave it in the comment field below. And to learn more about what's coming next from Transparent Physics and to help the channel grow, please click subscribe. All right, then this is an action-packed episode. We got to get going on it. So in terms of what we're going to get done today, we're going to understand what a conservation law is. We're going to apply the idea of conservation to kinetic and potential energy. Remember, our focus is just on gravitational potential energy for now. We're going to take a look at the conservation of energy equation, at least a nice generic version of it, and we'll even solve a simple problem, but it's going to be a problem we solved before. That'll make sense a little bit later. And in a recurring theme on this channel, we find that the science definition for conservation is maybe a little different than the everyday way we would use it, so let's find out. It's scientifically speaking, conservation means that some total quantity remains the same over time. And if that sounds a little familiar, if you've already had chemistry, conservation of mass is a very common application of it that you may have already been exposed to. Conservation laws are very powerful. If we know that there's a quantity that doesn't change, often that can give us a really important handhold to solve other aspects of the problem. Because if we know what this answer is going to be at the end of the problem, we can actually tag that into the information that we know and solve other parts of the problem more easily. In my opinion, there's no better introductory explanation for conservation of energy than the one from Richard Feynman. He was an American theoretical physicist, sort of cut his teeth on the Manhattan Project when he was a young physicist, explored the realm of quantum physics with much of his professional career, for which he shared the Nobel Prize in 1965. Also was a pioneer in quantum computing and nanotechnology. So it's just really a dizzying sort of intellect. But at the same time, he has this like New York accent and he sounds like the guy on the corner, and he just had this ability to take, very complicated concepts and just explain them in a very sort of down-to-earth manner. And very popular lecturer. He really had a passion for trying to get science out to the masses, out of the ivory towers, so everybody could try to understand it. So we're going to take a look at his classic lecture on the topic. And the clip is a couple minutes, so it's a good time to pause the video, brew yourself a nice cup of tea so that you can enjoy it while you listen to Richard Feynman explain conservation of energy.
I would like to make a kind of silly analogy to explain a little bit about it. And I want you to imagine that a mother has a very difficult child. Well, not necessarily difficult, but she has a child who she leaves alone in a room with 28 blocks. The indestructible, absolutely indestructible blocks, like the charges. And the child plays with the blocks during the day, and when the mother comes back, she discovers, indeed, there are 28 blocks. She checks all the time the conservation of blocks. Well, this goes on for a few days until one day when she comes in, there are only 27 blocks. One block she finds later outside the window. He threw one out the window. So first we must appreciate that conservation laws involve that you watch out that the stuff that you're trying to check doesn't go out through some water. And the same thing could happen the other way if a boy came to play with him and brought in some blocks. Of course, those are obvious technical matters that you have to be careful of when you talk about a conservation law. But now suppose, however, that when the mother comes to count the blocks, she finds there are only 25 blocks, but suspects that in a little toy box, in a box that the boy has, he has hidden the blocks. So she says, I'm going to open the box. He says, no, you cannot open the box. How can she tell? She's a very clever mother, unlike most. She would say, the box weighs, I know when it's empty, 16 ounces, and each block weighs 3 ounces, so what I'm going to do is I'm going to weigh the box. So she would have another thing, number of blocks 16 plus weight of box minus 16 ounces divided by 3 ounces. And that adds always the same to 28. Goes on for a while until it doesn't check. But you notice that the dirty water in the sink is changing its level. So we have the water level. Height of water in sink minus 6 inches, which it is when there's no block in it, divided by 1/4 of an inch, which is the height that the water rises when a block is in the dirty water. Now, as the boy becomes more ingenious and the mother continues to be ingenious, more and more terms must be added on here, which all really represent blocks, but from a mathematical standpoint are abstract calculations, which the blocks are not seen. Now I would like to draw my analogy and tell you what is common to this and the conservation of energy and what is different. Suppose that you never saw the blocks at all, that in any one of the situations there were never any blocks. Then the mother would be always calculating a whole lot of terms, which is called blocks in the box, blocks in the water, blocks and so on. But there are other differences that there aren't any blocks as far as we can tell. And that the numbers that come out here are not integers, unlike the case of the blocks with the child. Suppose, it could happen to the poor lady that when she calculates this number, it comes out 6 1/8 blocks. And when she calculates this number, it comes out 7/8 of a block, and the rest of them give 21, still 28. That's the way it looks. So what we discover is that we have a scheme in which we can find a sequence of rules, and from the rules, each one of the different kinds of calculations we call calculating the same thing, number of blocks, or energy, by different rules. And then we add all the numbers together from all the different forms of energy, it always adds up to the same total. But as far as we know, there are no real units. It's not made out of little ball bearings. So it's abstract. It's purely mathematical. There exists a number such that you can calculate and it doesn't change. I cannot interpret any better than that.
Again, just a stellar explanation of conservation of energy, and again, even as a 25-year plus physics teacher, I still appreciate the nuances of that presentation. A couple things to review in terms of what he talked about. We're going to assume for introductory physics we have what's called a closed system, the idea that no blocks, if you want to think of them quote unquote, energy enter or leaves. In this case, we're going to have 2 places where we can put the energy. He talked about like different places. He talked about, like the toy chest and the dirty dish, the dirty water. And, we're going to have 2 places energy can be quote unquote hiding. It's going to be kinetic energy or gravitational potential energy. That's it. As he noted, there was a certain number of blocks and that number had to stay the same. So the total energy is going to stay constant, but it can switch between kinetic energy and potential energy. And that's where the idea of conservation comes from. And ultimately what it really comes down to is when you're doing a calculation using conservation of energy, the total amount of energy is the same at the start and the end of the problem. Total amount of energy being measured in joules can be represented both by kinetic and potential, and whatever is lost from the one is gained by the other. Sometimes in class I'll have sort of 2 beakers, and I just sort of pour water between one to the other, and the water represents the amount of energy, and you can have some water in the kinetic beaker, some water in the potential beaker, but the total amount of water remains the same. So this equation, this calculation is going to help us express that mathematically. Let's take this kind of abstract idea and make it a little more concrete. We'll take a ball, we'll hold it at rest over the edge of a cliff. That ball, we're going to assume, is at a non-zero height. We'll assume a 0 height is at the bottom of the cliff. Remember, we can choose our heights in different ways. Doesn't really matter, but we'll just assume that it has a high gravitational potential energy to start, and since it's at rest, it has no kinetic energy. We drop it. As the ball falls, it speeds up. We knew that already, but from an energy perspective, as it drops, it's losing potential energy because potential energy is calculated using mgh. As h gets smaller, the gravitational potential energy decreases. So the representation of energy in the object from a gravitational energy perspective gets smaller. But as it drops, it speeds up. And the exact amount of energy that it loses from being dropped is what it gains in the form of kinetic energy. Kinetic energy is represented as the energy of the motion. Now, if we were to try this in the real world, and we looked for quote unquote the blocks of energy, we would find that we don't have all the energy just before impact that we did when we released it. Because in the real world, there's lots of places the energy can get siphoned off to. Just like as Feynman was talking about, there's lots of places those blocks can go. It doesn't mean they've been destroyed. It just means you have to be more clever in terms of how you find this. But a really common one would be losing energy to air resistance. But as has been the mantra this year, we generally ignore air resistance. And now that we've sort of got our framework that we will be looking at an object dropping, let's take a look at the concept of conservation of energy, and we'll sort of translate that into the equation we're going to be using. It's a very painless transition, trust me on this one. So the idea, if we want to boil conservation of energy down to its most basic form, we can simply say initial energy equals final energy. That's really what conservation is all about. And we've talked about, in the context of introductory physics, we're really only going to be looking at energy in two places. We're going to be looking at kinetic and potential. So initial energy is represented by the initial kinetic and the initial potential. Final energy is represented by the final kinetic and the final potential. And then we can take those and turn them into mathematical expressions. So kinetic energy is KEI, potential energy is PEI, etc. We can take kinetic energy and potential energy, turn those into the calculations that we've talked about earlier in this series. Kinetic energy is 1/2 mv squared, potential energy is mgh. And that expression is the most basic sort of formulation of conservation of energy that we'll be using. It looks a little big and a little bit ugly, but remember, those smaller terms are terms that we've seen before. And to be honest, a lot of times, at least one of these terms is going to drop out, and we're not going to need it at all. But let's see how that works out in a sample solution. And what we'll find when we're doing conservation of energy problems is the scenarios aren't necessarily going to be new scenarios. They're going to be the kind of things you've worked out before, say with kinematics or dynamics, but they're just going to be looked at through the lens of energy instead of, say, the kinematics equations or forces. It's the same ultimate scenario. We should get ultimately the same answers, but we're going to use a different perspective to solve it out. So back in the kinematics series, we did a solution on free fall, where a pot is knocked off a ledge, and instead of looking at that in terms of the kinematics equations, the Scooby equations, we're going to look at it instead with energy. So let's see how it is the same and different. So let's take a look at this problem. We are going to look at how the initial information as we write it with a conservation of energy solution looks a little different than how we would have written it for a one-dimensional kinematics problem. So all the information as listed would be as if we were solving this back when we were just doing the kinematic stuff. But let's take a look here. So a couple things we'll want to tweak, change, etc. I would say the first thing we want to take a look at is the idea of G. G is recorded as negative 9.80, and what we'll want to do is we're just going to leave that as 9.8. I generally reserve a negative sign in front of G when we're using the kinematics equations. That's it. Everywhere else, let's just leave G as a positive value. In addition, we have the displacement as negative 16.4. That is great for a kinematics problem. For conservation of energy, what we're really interested in is we're interested in the initial and the final. So we're going to get rid of displacement as negative 16.4. It's still entirely true, but what we're going to take a look at instead is we are going to go with the idea that we are looking at HI and HF. So HI, where we start at the top, let's get that a little thicker. So HI is going to be positive 16.4 meters. And we're going to say HF is going to be 0 meters because it's going to end at the ground. And then other than that, we have the initial velocity, and we want to solve for the final velocity. And what this problem is what we're going to look at when we look at this problem this time around is we're only going to focus on this second part. We're going to focus on what is its velocity at impact. So that is going to be a shorter problem than the one we worked before. When we solved it back in the kinematic scenario, we could have jumped straight into final velocity if we wanted to. So this solution is going to be shorter, but that's a little bit of an artificial construct just based on the way that we solved it before. All right, let's take a look here. So when we set up a problem like this, sometimes I'll even write the idea. Sometimes I'll just say initial energy equals final energy. Just to remind my students that that is the overriding principle that's guiding everything we're doing for the solution. So I also will write out every term to begin with, and then we'll drop out the ones we don't need as we go through it. So initial energy would consist of kinetic energy and potential energy, and then kinetic energy and potential energy for the final. And then I normally just expand these out into the variables while we're still learning what they all mean. So this is 1/2 mvi squared plus mghi equals 1/2 mvf squared plus mghf. And then we can take a look at the information we're given, and we can knock out some empty suitcases, as we say. The initial velocity is 0. So that means this term drops out, and that means the entire term gets eliminated here. And then we also know the final height is 0. So this term gets dropped out, and everything associated with it also gets eliminated. So we've already streamlined the problem quite a bit just by looking at the information that we're given. So we can rewrite this as simply mghi equals 1/2 mvf squared. Now here you might panic a little bit because in the initial problem we weren't given a mass. There's no the mass of the flower pot was not included in the solution or the initial information. So here it's asking us for mass, but remember, if mass appears in both terms, then we can effectively cancel mass out. Basically, we just divide by mass on both sides. And if we divide by mass on both sides, mass drops out. So whatever the mass of the flower pot was, or is, or will be, doesn't matter. It drops out. So it could be a tiny flower pot, it could be a big flower pot. We're going to get the same answer either way. And there should be some comfort with that, because when we solved this problem initially, back in the kinematic section, we didn't know what the mass of the flower pot was, but we still said, hey, this is going to be its velocity and impact. So that sort of implies the idea that in a sort of idealized world, the mass of the flower pot's not going to matter, because if it did, we would have had to include it initially anyway. All right. So we're solving for VF. So I'm going to rewrite this equation just to put the unknown on the left side, because that's how I roll. Solve for VF. In order to get VF by itself, we're going to multiply both sides by 2. We're going to take the square root of both sides, get VF by itself. And the equation we're left with is VF equals the square root of 2GHI. And that's it. We just have to plug and chug. That's solving it out. So here we're going to take 9.80 meters per second squared, not negative, positive. And also HI is going to be 16.4 meters. And off camera, I'll get on my calculator here. So we have square roots 2 times 9.8 times 16.4. And I get a final velocity of 17.9. And I realize it is asking for velocity, so velocity has a direction associated with it. Anytime you take a square root, there is a plus or minus in front of it, and then you sort of need to decide which of those is relevant for your situation, or maybe both of them are. In this case, it's definitely going to be a negative 17.9. So the velocity is going to be negative 17.9. In the context of a conservation of energy problem, a lot of times they'll ask you just for speed because that's what's associated with the kinetic energy more than the velocity itself. But just watch out for speed versus velocity. You might have to indicate the direction. And there we go. So that's how we go about solving that problem.
Oh, and there's your first conservation of energy solution. Oh, they grew up so quick. Hey, with conservation of energy available to us, we're going to revisit a lot of the older scenarios that we studied in kinematics and dynamics. And I think what you'll see is that using conservation of energy often provides a quicker, more elegant solution. Not always better, but often it's going to be something that's going to be worth your time to learn how to do. And as always, thanks for watching this lesson. Hopefully I, with the invaluable assistance of Richard Feynman, have made the idea of conservation of energy a little clearer for you on this lesson from Transparent Physics.